I want you to do something for me, just for a second. Close your eyes.
Okay.
I want you to try and strip away everything. The sound of the room you're in, the traffic outside, all of it. Just delete the world.
Where are we going?
We're going somewhere sound can't exist. To the interstellar medium.
The space between the stars.
Exactly. And I don't just mean, the space between Earth and Mars. I'm talking about the deep, deep void between our solar system and the next one over.
It's a place of almost unimaginable cold. Just a tiny fraction of a degree above absolute zero.
It's a graveyard of stillness, isn't it? The particles of dust out there are so far apart you could fly for 1,000 miles and not hit a single one. It is the quietest, most empty place in the entire universe.
It's not truly empty.
No, it's not. Because in this absolute silence, something is moving.
And it's not a planet. It's definitely not a star. It's this jagged, kind of ugly piece of ice and rock.
Just tumbling end over end in the blackness.
Yeah, and if you were floating right next to it, you probably wouldn't even see it. It's so dark.
Darker than asphalt, I read. It just swallows almost every bit of starlight that hits it. A ghost.
A ghost is a good word for it.
And this object, this ghost, has been drifting in that silence for, how long are we talking?
Millions of years, maybe.
Wow.
Maybe billions. It's a time scale that's really hard for the human mind to even process.
So this thing was created in a star system that is not ours.
That's right. It was probably kicked out during the chaotic birth of its own planets, slung out into the galaxy.
Wow. So it's seen things. It's traveled through the spiral arms of the Milky Way. It's witnessed stars dying, new nebulae lighting up, all before Earth even existed.
It's a cosmic time capsule, a message in a bottle floating on the biggest ocean imaginable.
And for all that time, for eons, its journey was completely alone. It didn't orbit anything. It just fell through the dark. But then something started to change. Very, very subtly.
Gravity.
The universal constant.
It started to feel the pull of something new, a new gravitational well.
And in the distance, one of those little pinpricks of light started to get brighter and brighter than all the others.
A yellow dwarf star, our sun.
And the object started to pick up speed. It was drawn in. It fell past the orbit of Neptune, completely silent, totally unseen.
Slipped right past Uranus, a frozen shadow against the backdrop of distant stars.
It wasn't until it got into the inner solar system that we finally saw it.
And that's where our story really begins.
Yeah.
Because this isn't just some random rock. This is Comet 3I Aglas.
And that designation 3I, that's important, isn't it?
It's a badge of honor. It means it's only the third interstellar object humanity has ever detected. A messenger from the void.
And unlike the ones that came before, this messenger didn't just fly by in silence. This one, it had something to say.
It spoke loudly.
So today, we're going to do a true deep dive into the journey of this messenger. We're not just going to skim the headlines. We're going to get into the nitty-gritty of the orbital mechanics that proved it was, for lack of a better word, an alien.
And then we'll look at the spectroscopy, the light that told us what it was carrying.
We're going to move from the cold, quiet surveillance of our telescopes to the absolute violence of its encounter with our sun.
And we should also touch on the debates, because the scientific community didn't just accept this. There were arguments. There were controversies.
Of course. This is the story of a traveler that crossed the entire galaxy to tell us something profound, that we are not alone in the chemical history of the universe. So let's start with the discovery. With the eyes that found it, we have to shift our view from deep space right back down to Earth to the top of a volcano in Hawaii.
This is the home of ATLAs.
The Asteroid Terrestrial Impact Last Alert System. Okay, I have to say, that is a terrifying name. Last Alert sounds like it's from a disaster movie.
Well, its job is literally to prevent a disaster movie.
Yeah.
I mean, ATLAS wasn't built to find these amazing scientific curiosities.
It was built for planetary defense.
Exactly. It's a network of robotic telescopes. They're in Hawaii, South Africa, Chile. They are our sentinels. They scan the entire visible sky every 24 hours.
Looking for bullets in the dark.
That's a perfect way to put it. They're hunting for near-Earth objects, NEOs, asteroids or comets that are on a trajectory that might, intersect with Earth.
So how does it work? It just takes pictures and looks for things that move.
That's the basic idea. The background stars stay fixed, but an asteroid will shift its position from one image to the next, taken minutes apart.
So on what was probably a totally normal night, a computer algorithm flags a tiny, faint smudge of light.
Right, not even a person at first. And to the naked eye, on the raw data, it would have looked like nothing. like a glitch, maybe a cosmic ray hitting the sensor.
That must happen all the time.
Constantly, satellite sensor noise. But this one was persistent. The astronomers who checked the data saw it was a real object.
Yeah.
But then it got weird.
How so?
When they tried to calculate its orbit, the map it broke. It didn't make any sense.
Okay, let's unpack that, because the math broke sounds like a really big deal. Everything in our solar system is supposed to follow the rules, right? Kepler's laws of planetary motion.
It has to. The planets, the asteroids, all the comets from our own neighborhood, they all move in ellipses.
An ellipse being a closed loop, a squashed circle.
Exactly. Imagine a tether ball swinging around a pole. No matter how far out it swings, it's attached. It has to come back. Gravity keeps it in this sort of repetitive dance.
And there's a number for that, right? A way to measure it.
There is. It's called eccentricity,
Yeah.
which we denote with the letter E. It's just a measure of how stretched out that orbital ellipse is.
So a perfect circle would be, what, 0?
An eccentricity of 0. And a really long, thin orbit, like a typical comet from our own Oort cloud, might be something like 0.9, maybe 0.95.
But it's always less than 1.
Always. As long as E is less than 1, that object is gravitationally bound to the sun. It is trapped. It will eventually return.
But when they ran the numbers for this new object for 3I Atlas,
The eccentricity was greater than 1. Significantly greater.
which means what? What does that shape even look like?
It means it's not an ellipse. It's a hyperbola.
Okay, so let's stick with the analogy. If the ellipse is a tether ball on a rope, what's a hyperbola?
A hyperbola is a bullet fired through the room. It comes in through one window and goes out through another. It's moving with way too much energy to be caught by the pole.
So the sun's gravity still affects it.
Oh yeah, it bends its path. It forces it to curve. But it cannot capture it. It's just a temporary deflection.
So the shape of that line, that trajectory, is literal proof that it's an alien object.
The shape and the speed, we have a term for it. Hyperbolic excess velocity. Basically, this object was moving at a speed that is physically impossible for anything that originated within our solar system.
It had a running start.
A massive running start. It wasn't just falling toward the sun. It was diving at it with pre-existing momentum from its journey between the stars. The mathematics were they were irrefutable. This thing came from out there and it was absolutely going back out there.
That is both terrifying and incredibly thrilling. It means we had one shot, one brief window to study this thing before it was gone forever.
A fleeting glimpse.
So as 3I Atlas raced closer, we started to get a better look at it. And this is where the debates really fired up, right? What was it? Was it an asteroid? Was it something else?
Well, it definitely wasn't a spaceship, no matter how much the internet wanted it to be.
Right.
But it also wasn't behaving like a typical asteroid. As it got warmer, as it flew closer to the sun, it started to change. It started to grow a tail.
Which is the classic sign of a comet. The old dirty snowball idea.
Well, let's pause on dirty snowball. It's a great term that Fred Whipple came up with in the 50s, and it's stuck because it's so evocative. But it's a little misleading.
How so?
If you were actually standing on the surface of 3I Atlas, it wouldn't look like a snowball at all. It would be a charred, black, alien landscape.
Because of all the radiation in deep space.
That's part of it, but it's mostly because of the carbon. We're talking about the nucleus, the solid core, which is probably a few kilometers across. And it's covered in this crust of very dark organic compounds mixed with dust and rock. It has an albedo of about 0.04.
An albedo of 0.04? What does that mean in real terms?
Albedo is just reflectivity. So, for comparison, fresh white snow has an albedo of maybe 0.8 or 0.9. It reflects 80 or 90% of the light that hits it.
Okay.
Charcoal has an albedo of about 0.04. This thing is blacker than coal.
It's a stealth comet.
It is, until it gets close to the fire. And this is where we get into the amazing physics of sublimation. As 3I Atlas crossed what we call the frost line, which is roughly out by the asteroid belt, the sun's heat started to cook that dark crust.
And in the vacuum of space, ice doesn't melt.
Exactly. You don't get puddles of water on a comet. The pressure is far too low. It goes straight from a solid to a gas. Boom! The ice that's been locked deep inside the nucleus for billions of years turns into gas almost instantly. It expands thousands of times in volume, and it just blows out through weak spots in the crust.
Creating jets, like geysers.
Like supersonic geysers, but shooting out gas and dust instead of water.
And that cloud of gas and dust is what creates the atmosphere around it.
That's the coma, a glowing fuzzy ball of gas. And then the solar wind, this constant stream of charged particles blowing off the sun slams into that coma and pushes the material backwards.
Forming the tail.
Forming the iconic comet tail. or tails, really. There's usually a dust tail and a separate ion tail.
But we didn't just look at this with regular visible light telescopes, did we? We have some more advanced tools now. I was reading about the results from the SphereX mission.
Ah, yes. The spectrophotometer for the history of the universe, epoch of reionization, and ICES Explorer.
That is a mouthful.
Astronomers love a good acronym. But SphereX is a game changer. It's a space telescope that sees the universe in infrared light. It sees heat signatures.
So what did it see when it looked at 3i Atlas?
It saw something the other telescopes missed. It detected this massive, glowing envelope of dust surrounding the comet.
An envelope, like a bubble.
More like a halo. It was the heat signature from all the tiny dust grains being warmed up by the sun. It told us that this object was incredibly active. It was shedding its ancient skin at a furious rate.
And that was important because it meant we could analyze what it was shedding.
Exactly. We could figure out what this visitor was actually made of.
Which brings us to the main event, the encounter. The moment it reached perihelion.
The point of closest approach to the sun.
The moment of truth. Because let's be honest, a lot of comets don't survive this. They get too close to the sun and they just, poof, they fall apart.
We call them sun grazers, and you're right, many of them completely disintegrate. The sun is a nuclear furnace. The radiation pressure alone is immense.
And the gravity's trying to tear it apart too, right? Tidal forces.
Exactly. The side of the comet nucleus, facing the sun, is being pulled much more strongly than the side facing away. It tries to stretch the object until it breaks. You remember Comet Ison from a few years ago?
Oh yeah, the comet of the century, that was it.
The very one. It dove toward the sun with all this hype, and it just evaporated. A cloud of dust was all that came out the other side. There's a very real fear that 3i Atlas, being a relatively small object, might suffer the same fate.
So describe the motion for me. It's not just getting close, it's doing that slingshot maneuver.
It's a gravitational hairpin turn. The sun's enormous gravity grabs the comet and just whips it around. It accelerates to its absolute maximum velocity. We're talking hundreds of kilometers per second. It rounds that bend, skimming the solar atmosphere, and then it's fired back out toward deep space.
And the whole astronomical community was watching, holding its breath. Did it survive?
It did. It came around the other side, intact. But then it did something really weird.
Weirder than coming from another star.
Weirder than that. See, normally as a comet flies away from the sun, it should start to fade. It's getting further from the heat source, it's cooling down, the sublimation should stop, the tail should vanish, it should go back to sleep.
That makes sense. You walk away from the campfire, you stop sweating.
3i Atlas did the exact opposite. After it passed perihelion, as it was already moving away from the sun, it suddenly brightened. Dramatically, it flared up.
Why would it do that?
We call it late outgassing. The leading theory is that the intense heat from the close approach didn't just warm the surface. That heat began to soak deep into the nucleus, into the core.
And it takes time for heat to travel through rock and ice.
A lot of time. So maybe weeks after its closest approach, that pulse of heat finally reached a deep, protected pocket of highly volatile ices, something that had been buried and shielded for billions of years.
And the pressure cooker just exploded.
That's the idea. The pocket ruptured. A massive amount of fresh primordial material that had been shielded since the birth of its home star was suddenly blasted out into space.
And this is where the science gets really, really good. Because we didn't just see the flare-up, we could analyze the debris from that explosion.
We could use spectroscopy.
Okay, I want to slow down here because this is the part that always gets glossed over in the news reports. Scientists find water. Great. But how? You can't just fly out and dip a test tube into a comet that's 100 million miles away.
No, you certainly can't. We do it with light. Spectroscopy is, at its heart, the study of how light and matter interact. So imagine light from our sun travels out, hits that gas cloud around the comet, and then some of that light is reflected back toward our telescopes.
Okay.
The atoms and molecules in that gas cloud, the water, the carbon, whatever's in there, they will absorb very specific frequencies or colors of that sunlight.
Like a filter, each molecule has its own specific color that it blocks.
It's a perfect analogy. So when we take the light that comes back to us and pass it through a prism, or more accurately, a diffraction grating in a modern telescope like the James Webb Space Telescope.
You get a rainbow.
Yeah.
A spectrum.
You get a rainbow, but it's a rainbow with gaps in it. It has these dark lines where the light has been absorbed.
And those dark lines are chemical barcodes.
They are the fingerprints of the elements. Hydrogen has a very specific pattern of lines. Carbon has a different one. Water, H2O, has a very distinct and undeniable signature, especially in the infrared part of the spectrum.
So when the team pointed the instruments on the Webb telescope at this outburst from 3I Atlas,
They saw the barcode for water, unmistakably.
water from another star system.
Tons of it. I mean, 3I Atlas was literally spraying water vapor across our solar system.
Okay, so here's the million-dollar question. Is it our kind of water? I remember from other comet stories that there's this thing called the deuterium to hydrogen ratio, the DH ratio. This is like the forensic evidence, right?
This is the critical metric. It's the smoking gun for planetary science.
Mm.
So as you know, water is H2O, 2 hydrogen atoms, 1 oxygen. But very rarely, a hydrogen atom can have an extra neutron in its nucleus. We call that deuterium, or heavy hydrogen.
And the water it forms is heavy water.
Exactly. So the ratio of normal hydrogen to this heavy hydrogen acts like a kind of cosmic return address. Earth's oceans have a very specific DH ratio.
And the comets from our own solar system, from the Oort cloud, they usually have a different ratio, don't they?
That's right. They often have a much higher ratio. Their water is heavier than ours, which has been a big problem for the theory that comets delivered Earth's water.
So if 3I Atlas had a DH ratio that was different from Earth's, it would just be another piece of evidence that it's an alien object.
Well, we already knew it was alien from its orbit. The DH ratio tells us about the environment where it formed, the temperature, the radiation levels in its home nebula. So the data came in, and the ratio for 3I Atlas was surprisingly close to Earth's.
Wait, what? It matched us.
It was within the statistical error bars. And that
Yeah.
that is a bombshell of a find. Because, as I said, for a long time, the argument against comets delivering our water was that the local comets we'd studied were a poor match. Their water was too heavy. And then here comes this object from a completely different and unknown star system, and it's carrying water that looks a whole lot like the water in our oceans.
That feels like it changes everything, and it leads us directly to the big, almost sci-fi theory of panspermia.
I knew we'd get there.
We have to. It sounds fantastical, this idea that life, or at least the seeds of life, is just distributed throughout the universe by comets and asteroids.
It's a term that comes with a lot of baggage, so let's strip away the little green men part of it and just talk about the chemistry. Panspermia, in a hard science context, is simply the theory that the ingredients for life water, carbon-based molecules, amino acids, aren't necessarily made on planets. They are delivered from space.
The cosmic pollinator theory.
A great way to put it. We know that Earth formed in a very hot, dry part of the early solar system. Any water that was here originally should have boiled off into space. So where did our oceans come from? Why are you and I mostly water?
The late heavy bombardment.
The leading theory, yes, that about 4 billion years ago, the early Earth was absolutely pummeled by a storm of asteroids and comets from the outer solar system. They were the water trucks. They delivered the volatiles.
And 3IA tells is like the proof of concept for that delivery mechanism.
It is a proof of concept on an interstellar scale. It proves that these objects are cargo ships. And it wasn't just shipping water. The JWST analysis also found hydrocarbons.
Okay, explain what that means. What kind of hydrocarbons are we talking about?
Things like acetylene, methane, ethane, simple chains of carbon and hydrogen atoms. Now, it's really important to stress that organic in astronomy does not mean alive.
Right, it doesn't mean we found bacteria.
Not at all. It just means carbon-based chemistry. We found the Lego bricks of life.
The flour and the sugar and the eggs, but not the cake.
Precisely. But finding the flour and eggs on a rock that has traveled from an entirely different star system it's profound. It means that the basic chemistry needed for life isn't unique to us. The universe is saturated with these ingredients.
And there was a study, right, in Nature Astronomy that connected this to bigger things.
Yes, the paper made the point that the chemical signatures we saw in 3I Atlas are the same signatures we see with our telescopes in star-forming regions light years away. In the hearts of distant galaxies, this comet just brought a physical sample of that chemistry right to our doorstep for us to study up close.
I want to push back a bit, though. Let's talk about the other visitors. The first one, Oumuamua, back in 2017, that thing was just bizarre.
An anomaly in every sense of the word.
It was dry, it had no tail, it was shaped like a cigar or a pancake. It was nothing like this. Why was it so different?
That is the great puzzle, isn't it? Oumuamua was tumbling. Weirdly, it was elongated, and yes, it appeared to be completely inert. No water lines, no coma, nothing. It was so strange that some credible scientists like Avi Loeb at Harvard seriously proposed that it might be an artificial object.
The solar sail theory, yeah, because it accelerated in a way they couldn't explain.
Right. But then, a couple of years later, we found the second one, 2I Borisov.
Mm-hmm.
And Borisov looked Well, it looked like a perfectly normal, pristine comet. It had a coma, a tail, everything you'd expect.
And now we have 3I Atlas, which is also clearly a comet, but a very wet one that behaves strangely.
Exactly. So it seems like Oumuamua was the real odd one out. It suggests that the population of interstellar objects is incredibly diverse.
So just like our own solar system has rocky asteroids and icy comets and metallic objects, the galaxy is just throwing a whole mix of stuff at us.
It seems so.
Yeah.
And 3I Atlas represents that icy, volatile-rich population, the water bearers.
It really makes you wonder how much of this stuff is out there. I mean, we've only ever spotted 3.
We've only seen 3, because we only just recently put on our glasses. This is what people are calling the golden age of observation. For billions of years, these objects have been flying through our solar system, completely unnoticed. We were just blind to them.
It's the streetlight effect. You can only find your keys where the light is shining.
And our light is getting so much brighter. It's the ATLAS network, the Pan-STAR survey in Hawaii, the upcoming Vera Rubin Observatory in Chile. We are scanning the sky with a depth and a frequency that was science fiction 20 years ago.
So what's the estimate? How many are out there?
The current model suggests that at any given moment, there is at least one interstellar object inside the orbit of Mars.
Wait, one right now, as we're speaking?
Statistically, yes. They are buzzing around us like cosmic flies. We just miss most of them because they're small, they're dark, and they're moving incredibly fast.
But now that we know what we're looking for, we're going to find more.
Many more. And that changes the mission. We're moving from an era of just discovery to an era of interception.
You mean actually catching one?
I mean, chasing one down. The European Space Agency, ESA, has a mission in development right now called the Comet Interceptor. The concept is just brilliant.
So what's the plan?
Instead of waiting until we find a target and then trying to build and launch a rocket, which takes years and you'd miss it.
Right, the object would be long gone.
Exactly.
Yeah.
So they're going to launch a spacecraft first and park it in a stable spot in space.
Like a police officer waiting in a speed trap on the highway.
A perfect analogy. It will just sit there, dormant, at a place called the L2 Lagrange point, and it will wait. When the ground-based telescopes find the next 3I Atlas on a suitable trajectory, the interceptor will get the call. It will fire up its thrusters and fly to meet it.
That's incredible. So it would do a flyby?
A very fast flyby, yes. It would even deploy smaller subprobes to get multiple perspectives, maybe even fly through the coma to sample the gas.
But you said these things are moving at hyperbolic speeds, faster than anything we've ever built. How can a chemical rocket even hope to catch one?
And that is the huge engineering challenge. That's the bottleneck. Our current propulsion, burning chemical fuel, has a fundamental speed limit based on its exhaust velocity. To really chase down a fast-moving interstellar object, or even think about a sample return mission, we need something new.
Like what? Solar sails.
Solar sails are a possibility. Or maybe advanced solar electric propulsion. There was even a recent paper proposing something called a statite, a satellite that uses a solar sail to just hover in a fixed position relative to the sun, ready to drop onto an intercept course at a moment's notice.
It really feels like we're on the cusp of a whole new kind of exploration. Instead of spending centuries to go to the stars, we're just going to wait for the stars to send pieces of themselves to us.
That's a beautiful way to think about it. We could potentially analyze the primordial material of an exoplanetary system without ever leaving our own solar neighborhood. Imagine landing a probe on one of these things, scraping up that ancient black dust and bringing it back to a lab on Earth.
We could find out the age of another star system.
We could look at the isotope ratios with perfect precision. We could search for complex amino acids. It would be a revolution in astrobiology.
But for 3A Atlas specifically, that shit has sailed. Or that comet has flown, I guess.
It has. The encounter is over. It's on its way out.
So let's talk about the departure. Because to me, this is almost the most poetic part of the whole story. It came, it screamed past the sun, it spilled its chemical secrets, and now it's just leaving.
It's moving away from the sun now, constantly,
Really?
speeding back toward the void it came from. As we watch it, it's getting fainter every single night.
Show is over.
The show is over. The coma will dissipate as the temperature drops. The tail will disconnect and just drift away, becoming part of our solar system's background dust. The nucleus, that dark mountain of ice and rock, will freeze over again. It will go back to sleep.
Does it leave anything behind, though? A calling card?
It leaves its trail. The dust and the gas that it ejected during that violent encounter will continue to orbit the sun for thousands of years. It has literally added its own mass to our zodiacal cloud. So in a very real sense, a tiny piece of that alien star system is now a permanent part of ours.
And the object itself, Where is it headed?
Back to the void. Its trajectory is pointing roughly toward the constellation Pegasus. But the odds are it will never hit anything. The galaxy is just too big, too empty.
Yet you will just wander for another billion years.
Perhaps. It might have a distant encounter with another star, but it will likely never again pass this close to a source of heat. It's returning to the deep freeze.
It really is a ghost, a survivor.
Think what it's been through. The violent ejection from its home, the unimaginable cold and loneliness of interstellar space, the searing heat and gravitational torture of passing our sun. And now, the long goodbye. The return to the dark.
It can't help but make you feel small.
It's the ultimate pale blue dot perspective, isn't it? We sit here on our little rock, worrying about our daily lives, while these cosmos leviathans drift past, carrying the actual history of the galaxy on their backs.
But there is a flip side to that, I think. We are small, yes, but we are also the ones who are watching. As far as we know, we're the only ones in the solar system who even noticed it go by.
That is the human paradox. We are physically insignificant, but our curiosity is infinite. We built these incredible machines, Atlas and Syrinx and Webb, just on the off chance we might see something like this. Just to try and answer that one question. Are we alone?
And 3i Atlas gave us an answer, of a sort.
It did. It said you are not alone in your chemistry. The water in your oceans is the same stuff you'll find in the void. The building blocks are everywhere.
I want to leave our listeners with one final thought to chew on. You called 3i Atlas a time capsule, a message in a bottle from some other world.
Yes.
Well, we're sending out our own messages, aren't we? Voyager 1 and Voyager 2, New Horizons, they're all on escape trajectories now. They're leaving our solar system forever.
They are our own man-made interstellar objects.
Exactly. So fast forward 4 billion years, our sun is a red giant, the Earth is a cinder, but the Voyager probe will still be drifting, silent, through the dark, and maybe, just maybe, it will happen to pass through another star system. Maybe it will get close enough to their star that it heats up. Maybe its metal antenna outgasses some tiny bit of material.
And maybe some other intelligence on some other world will look up. They'll see a faint smudge of light that's breaking all their rules of orbital mechanics, and they'll point their instruments at it. And they wonder who sent it.
We are the aliens of the future.
That's a haunting thought. But it's also a deeply hopeful one.
3i Atlas was a knock on the door from a stranger. It's gone now, receding back into the deep interstellar night. But for that one brief moment, we reached out and we touched the stuff of another star. And that has to change how we see our own little precious place in the dark.
The silence of the void returns. But this time, we're listening. We know what to look for now.
Thank you for listening, and keep watching the dark.